Hello and welcome to day 5, our last day of the unit. We'll get right into it. If you look here, we have the integral from 0 to 2 of x parentheses x squared plus 1 to the 5th. Notice what method we're going to use. Well, you really only know one method, so we'll use u sub. So there's going to be two ways to do this. I'm going to show you one way, and then another way. Hopefully you'll find the second way a little quicker. So u to equal x squared plus 1, du to equal 2x dx. And so we'll know that du over 2 equals x dx. And then, knowing that, we can state that this, if that equals that, we know that we then have 0 to 2 of 1/2 out in front, x to the 5th, u to the 5th, du. And then we know that that's 1/2 u to the 6 over 6 from 0 to 2. And we can say that that's 1/12 u to the 6 from 0 to 2. And before we can evaluate from 0 to 2, we need to actually take what u is. So we can say that this is x squared plus 1 to the 6 from 0 to 2. Because you can't evaluate in terms of u. And then we'll get 1/12 of, and if we do some math here, we'll get 5 to the 6 minus 1 to the 6. Noticing that 0 plus 1 is 1. And that will get us, let's see here, 15625 minus 1, which will give us 1302. So again, hopefully this is all coming back. We used u substitution, easy integral of u to the 5th, which is u to the 6 over 6. I pulled out this 1/6 to make it 1/12, and then evaluated. Hopefully this method will show you a way to be a little quicker here. So one of the methods that you can do when using u sub is to change the bounds. And so we're going to have our lower bound and our upper bound. And if I change them, I'm going to use them into u. I plug them right into u. So I'm going to get 0 squared plus 1, which is 1, and 2 squared plus 1, which is 5. Now, here's the reason why I want to do this. If I change the bounds using u sub from 1 to 5 of u to the 6 du, what I don't need to do now is actually plug in. I can keep it in terms of u. So you'll see that I'm going to get u to the, that's a 5 there, u to the 6 over 6 from now 1 to 5. You'll notice that I have 1/2 is still out in front. 1/12 u to the 6 from 1 to 5, and you'll notice that when I do that, I'm going to get 5 to the 6 minus 1 to the 6, and that's exactly what I have right there. But the reason now why I wanted to change the bounds is I didn't need to plug u back in. So hopefully you'll find that to be a little easier, especially with this one. So I'm going to let u be, well, what do you think? Hopefully you can see that that's sine of 2x all raised to the 5th. So hopefully use sine 2x. Let's see if it is. Du 2 cosine 2x dx. And so we'll get, we just want regular ones, so we'll get du over 2 to equal cosine 2x dx. So I can rewrite it, and I'll come over here and let's just change the bounds right now. We got 0, and we have pi over 8. So let's see what we get. We get sine of 0, which is 0, so that one didn't change. It's going to be sine of pi over 4. Well, where's pi over 4? Pi over 4 is 45 degrees, so it's square root of 2 over 2, or 1 over square root of 2. Either one. So now, we're going to get 1/2 the integral from 0 to square root of 2 over 2. Of u to the 5th. And du. So we're going to get 1/2 u to the 6 over 6 from 0 to square root of 2 over 2. And we'll get 1/12 of u to the 6 from 0 to square root of 2 over 2. And so we are going to get, well, that's going to be 2 to the third over 2 to the 6th, which will just leave us as 1 over 12 times 2 to the third, so 12 times 8, 1 over 96. And hopefully, I know I did that somewhat fast, hopefully you'll realize that by changing the bounds, I didn't need to plug back in any trig functions, which you know makes life difficult. This did not make life difficult. If you can not read my handwriting, the square root of 2 over 2 here and there. And then, how did I get this? Well, I know square root times square root will give me 2, so you can really raise that to the 1/2, and 6 times 1/2 is 3. And so there's that problem. Let's look at the next one. Why don't you guys try this one on your own? And so hopefully you got 2/3 times 8 minus 2 square roots of 2, or you could have written it out as this. Either one is correct. I leave it as that. I think it's more simple, but it doesn't matter to me. So again, what did we do? We found what du was. Luckily, du was a nice one, so we didn't have to divide that by anything. We changed our bounds. This is what you guys are always going to forget. And you can't forget it using u sub. It's always on tests and whatnot. So 0, ln of 3, we plugged in. 1 plus e to the 0 is 1. E to the ln of 3 is 3. That's where I got 2 and 4. And then look at how much simpler this was. We're just taking the integral of u to the 1/2 from 2 to 4. That's it. And so, did that out, and hopefully you got that. With this one, what do you think? We'll let u be 1 minus x. So du equals negative x, or negative 1 dx. So I got to divide by negative 1. Our bounds, got to change, can't forget that. So we got 0, we got 3/4. So we're going to get 1 minus 0, which is 1, 1 minus 3/4, which is 1/4. So we will get the integral from 1 to 1/4. Notice what happened here. We have a bigger number in the lower bound now, so we know it'll be negative. Negate it due to this negative here of 1 over u du. Well, we know that this is really saying the negative integral of 1 to 1/4. We know what the integral of 1 over u is, which is the ln of absolute value of u from 1 to 1/4. So what are we going to get? Negative parentheses, ln of 1/4 minus ln of 1. And ln of 1 goes to 0, so you get negative ln of 1/4. Done. Some of you may be wondering where the absolute value sign is. The absolute value of 1/4 is just 1/4, so we can drop it there. So that's why you don't need the absolute value sign there. So we're talking about long division. Long division, if I gave you 162 divided by 5. So what would we do? Well, we say, how many times does 5 go into 1? It can't, so then we look at the next number over. So how many times does 5 go into 16? 3. 3 times 5 is 15. We get 1. We subtract that. We bring down the 2. How many times does 5 go into 12? 2. It's 10. Subtract that. We're going to get 2, so we get a remainder of 2. So that's long division. We're going to do the same thing in these two. So we've got x plus 6 divided by x minus 3. So we're going to go x plus 6 divided by x minus 3. How many times does x go into x? That's what you got to look at. We don't care about the variables right now. We care about the highest, or the leading term, I guess I'll say, leading variable. So x times 1 is x, so x minus 3. We're subtracting that. X minus x is 0. 6 minus negative 3 is 9. So you get remainder 9. So x minus 3 goes into, excuse me, x plus 6 once with a remainder of 9. Let's just try this one. When you have no other variables, I can always write out kind of placeholders. We know those are all zeros, so we'll look at this. How many what can you do, what can you multiply to 2x squared to give you x cubed? And the answer is 1/2 x. That'll give me x cubed. So 1/2 times 2 is 1. X times x squared is x cubed. Then I'm going to multiply it to this one. 1/2 x times 1 is 1/2 x. And I'll subtract it. I know I have 0x squared there. I'm just going to get negative 1/2 x. And there is nothing that I can multiply 2x squared by to give me negative 1/2 x unless I use a negative exponent. We cannot do that. And so this is actually our remainder. So our answer to this would be 1/2 x remainder, okay, 1/2 x. Make sure that's a negative 1/2 x. So what was the idea of doing this? Well, what I did not do, and I should have, is written out what that equals. So we know x plus 6 over x minus 3 equals, and if you remember from Algebra 2, we're going to get 1 plus the remainder over x minus 3. Or in this case, x cubed over 2x squared plus 1 equals 1/2 x minus 1/2 x all over 2x squared plus 1. Now, why do we do this? Well, let's look. We have a nice couple integration problems. And so I can't use u sub. We have no idea how to do this. You can't split it up. So we're going to take what it was when you actually divided it by. We can say this actually equals 1 plus 9 over x minus 3 dx. I didn't change the problem. I just rewrote it as long division would have written it out. Well, I know that's the integral of 1 dx plus the integral of 9 over x minus 3 dx. And I can say that is equal to x. In this one, I can bring a 9 out, so I could really rewrite that as 9 over 1 over x minus 3. If I let u be x minus 3, du be dx, you'll notice I get 1 over u. And so I can say that this is plus 9 times the natural log of x minus 3 plus c. So I know I did that quick here, but you'll get 9 the integral of 1 over u du, and then that's ln of absolute value of u, and I plugged u back in. So that's where I got that. Looking at the last problem here, so I can rewrite that as the integral from 0 to 1 of 1/2 x minus 1/2 x over 2x squared plus 1 all dx. And I'll rewrite that 0 to 1 of 1/2 x dx minus the integral of 0 to 1 of 1/2 x over 2x squared plus 1. So this one I can do. I'll get 1/4 x squared. But what about this one? Well, this one's a little more interesting, isn't it? I can bring this 1/2 out in front, which will then give me 1 over 2x squared plus 1, x there. And if I let u equal 2x squared plus 1, notice that du equals 4x. Well, if I just divide by 4, it gives me my x up on top. And I also need to change my bounds. As I said, you will probably forget it. You need to forget it. So try to change those bounds, see what you get. I'm running out of time, so I'll do it out for you, and then you can look at it. And so our final answer is that. Take a minute to look. I've got one more page with 30 seconds to go, so we'll get to that. And so here is the final page. I know this is going to look intimidating. Please take the time to go through it. Notice that to make it look like any one of these inverse trig functions, you have to complete the square. And then notice that I just switched this. It should say probably 1 plus x plus 1 squared. This one's the more difficult one. Take out a 2. You have to leave the negative in there because you don't want it to be imaginary. Take out the 2, complete the square. Notice that this negative does distribute over to this